Hi, good evening. You are able to hear me? Oh, good evening. Yeah. So today is the first live interactive session of the NPTEL class. So I thought I'll start by introducing myself. So I'm Nandini. I'm a PhD student. I'm doing my PhD at IIT Bhubaneswar. So I'm currently in my fifth year. I'm about to finish. So I have done my MSc in meteorology from Cochin University of Science and Technology, Kerala. After completing my MSc, I have joined here for PhD. I mostly work on urban climate, like using modeling. We are trying to find the temperature and rainfall changes for each city. So that's the basic idea about me. So I will be handling this live interactive session for this course. So I will be having these sessions every Saturday from 6 to 8. So we will be mostly solving, I'll be mostly helping you solving the assignment questions, whatever is uh, being given in the NPTEL site that you have to submit every week. So I hope we'll have a good time. So if you have any doubt, you can always contact me. Um, uh, and I will try to help you if I know the answer. Okay. So yeah. So that's all about me. If you guys can also introduce yourselves, that will be good because since it is our first class, we can just get to know each other. What is your background and what are you currently doing and where are you from and all those things. Yeah. So if anyone wants to start, you can start. Or if you want to text in the, just type in the chat. That is also fine. If you don't want to speak, that is also fine. You can just type in the chat. So anyone want to start or good evening? Okay. Okay, great. So you have completed your PG. Okay, now you're currently doing PhD. And okay. And what was your MSc or MTech? Like what was your PG? You did completed your PG? MSc Physics. Okay. 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 Uh-huh. Oh, okay. This okay. Okay, I'm also not pretty sure about the direct relation, but there have been a lot of research that has been going on. Okay, yeah, yeah, got it. Yeah, okay. So, from what I understood, it's like warming climate is leading to rise in pathogens, virus infections, and all those things, right? Okay, yeah, yeah, I got the question. So, that is, I will actually have a look at it and then tell you because I'm also not pretty sure like how actually it directly affects. But recently, I have also seen many studies which actually relate this climate and health. A lot of research is going on in that area of the field actually. I'll surely look into it and I'll give you a answer. Is that fine by next week? Yeah. Just remind me next week. I'll surely have a look into it and I'll tell you. Yeah. Thank you. Yeah. Mm-hmm. 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 Okay. Climate is basically it is just an average of the variables which is taken over a large period of time, generally like 30 years or something. So suppose, and this is actually we are talking about a particular region. So this particular region can be as big as the whole earth, a continent, a country, or whatever it may be, or it can also be as small as a city. So we are considering like smaller geographical regions. So as we are talking about how the climate of a city has been particularly changing over the last few years or something kind of like that, we generally tell as local climate. So it just means that we are actually considering a smaller region like over a particular region. Suppose over a forest, how the yeah. Oh. So yeah, all the best for your PhD, Mr. Thank you for introducing yourself. And then we have yeah. We have Monica. Monica's BTech Computer Science graduate from Punjab University. I want to learn about climate modeling, so I joined this course. Okay, that is great. Okay, you are from a computer science background. Interesting. And I think we have two more people, Nitin and Pradha. You can introduce yourself or you can just type in the chat also. Just yeah. Hi Nitin. Okay. You are pursuing BSc Maths. Oh, great. So we have people from different backgrounds, I guess. We have computer science, we have physics, maths, and yeah, Pratap, you are from which background? Okay, you are okay. Diploma in engineering. Okay, nice. Okay, well, thank you for introducing. Yeah. So I think we'll start today's class. So today I was thinking I'll just give an overview of whatever has been already taught in your NPTEL class, and then we will try to solve. Like as we mm, go ahead in the class, we'll try to solve one or two problems as well. So yeah. So we will start with the basic definition of what is weather and climate. So you guys will would all maybe would already be familiar with these terms. So weather is basically the short-term atmospheric conditions. So when we talk about like the temperature in a day, or like when we generally say that it is a hot day or it is a sunny day, it is um, it is raining out and all these things, we generally refer to the weather of that particular region. So what we are experiencing on that particular day over very short period of time. So it could be whatever we are experiencing for few hours, days, or maybe weeks. This is the time scale that we are talking about when we are discussing weather. And so when we say that the temperature is 35 degrees Celsius, today the temperature is 35 degrees Celsius and it has been a hot day, we are generally talking about the weather. Okay. Now when we talk about climate, so in terms of climate, climate is basically the weather of a specific region which has been averaged over a larger period of time. Averaged weather of a particular region is basically known as climate, and it generally refers to long-term changes like 30 years or so. Minimum like 30 years. So when we talk about climate, so we know that we generally expect rain in the month of July over India, right? So June, July, August, we generally consider it as monsoon season, or that is when we experience rain. That is a general phenomena that we have been experiencing for a longer period of time or for a larger period of time. So generally we expect rain conditions in July and we expect summer or hot conditions in May. So these cases that we already know or whatever we have been experiencing for a long period of time is the climate of the region. So when we say that it is generally rainy season during July, we are talking about climate. And when we say that it is summer during May, we are generally talking about climate. So that is basically the difference between weather and climate. And weather can change from 1 minute to another minute or hour to hour or day to day or whatever it may be. And climate is basically the average of weather over time and space. And we generally define weather and climate using different variables. So we use different variables to define the climate and weather. So some of the variables, atmospheric variables that we use is temperature, rainfall, humidity, etc. Now, so this is basically climate and weather, and we use different kind of variables to define the weather of a particular day or a climate of a particular region. Now, I'll just introduce you some technical terms that we use to define the climate and weather. First one is climatology. What does it mean by climatology? So climatology just means the study of long duration of these. Climatology is the study of long duration statistical properties of atmospheric weather. Yeah, 30 years actually, it is kind of like the minimum time period that we generally use when we talk about climate. So, suppose if we have temperature or rainfall data for the last 30 years and we average the values, and whatever the value we are getting is basically the climatology or the climate of that particular region. 30 years is generally what we takes to do the average when we talk about climate. So, climatology is basically the study of long duration statistical properties of atmospheric weather data. Suppose we have temperature. Um, suppose we have last 30 years of temperature. It is like a huge data. So we do like different statistical like mean, standard deviation, maximum, minimum, a lot of things. So different statistical properties of that particular data set we analyze. So that particular study is known as climatology. So climatological study is the study of long duration statistical properties of these weather data, whatever we have like temperature, rainfall, pressure, etc. Now, among the climatology, once we do the statistical analysis, different terms are used to define the nature of the given climate data. So normals are basically normal. Normals means the mean or expected value values of weather. Mean or expected value of weather variables over a long period. Maybe 30-year average of temperature, precipitation, etc. over a particular geographic location like a city, a whole continent, or even the entire planet. So suppose if we have last 30 years of annual average temperature over a particular city, if we find the mean of the that 30 values, we get the normal temperature of that particular region. Suppose if in Bhubaneswar city we have the last 30 years of data, so it will be different for each year, right? If we take the average for each year, it will be different, and we have 30 different values. Now, if we take the average of those 30 different values, we get the normal value or the mean or expected value of that particular of the temperature of that particular region. So those mean are basically known as the normals. So normals basically refer to the mean or expected value of weather. Now there is another thing called as the variability range. Variability range means, as I said, suppose if we have 30 different values, we will have a particular standard deviation or range of those values. So we can say that the value ranges from, suppose if we get the average temperature is 35 degrees Celsius over Bhubaneswar city. I'm just giving you an example. Suppose we have last 30 years of temperature data over Bhubaneswar city. We took an average. Now we have the normal value of the normal temperature value over Bhubaneswar, and the value is 35 degrees Celsius. This 35 degrees Celsius we obtained from averaging 30 different values. So for that 30 different values, we will have a range. Suppose the values varies from 25 to 45, but we will have a standard deviation. So those particular parameters like variance, range, or standard deviation of the variables or of the parameter is basically known as the variability range. So variability range refers to the range of variation of the value. Range of variation in the value. Could be variance. It could be standard deviation. Or range. So that is variability range. Now we have another term which is known as the extremes. So now, when we look at some years would have experienced very high value of temperature. So suppose some years are reporting a temperature of 45 degrees Celsius, and some years are reporting a temperature of 20 degrees Celsius. So this is very far from the mean, right? So these maximum or minimum values, or like these extreme values, or very rare occurrences, are basically known as extremes. So extremes refer to the extremes of the weather property over a time period. For example, maximum temperature. Suppose maximum temperature of the last 30-year period or maximum precipitation rate of a 30-year period is basically known as the extremes. And then we have frequencies. So frequencies basically mean how many times a particular value occurred. Suppose if we have three years, the region recorded a temperature of 20 degrees Celsius, which means the frequency of that particular um, occurrence is 3. So like that, how many times? So generally this is used for extremes to say that over the last 30 years, 2 years experienced a temperature of greater than 45 degrees Celsius, or like 3 years we experienced a very extreme rainfall which is greater than maybe some millimeter or something. So frequencies are generally used to say how many times a particular event occurred. So that's why we use frequencies. Generally it is used for generally it refers to extremes only, like how many times a particular extreme event occurred, an extreme temperature event, an extreme rainfall event, or anything kind of like that. So that is frequency. So I hope that it is clear. So basically climatology means the study of long duration of the statistical properties of atmospheric weather variables. And there is normals. Normals mean the mean value of that particular variable. Variability range is how that particular variable is varying over the last 30 years. And then we have extremes, which basically refers to the maximum or minimum values of that particular data. And then we have frequencies, which generally refers to the number of times a particular event occurred, or number of times we recorded this much temperature, or number of times this greater than this much rainfall was received over the region. So that is basically known as a frequency. So these are just general terms that we use when we refer to climate or weather. Now, what are the different zones in the earth that actually influences this climate? What all things actually influences the climate? So when we look at earth, there are different spheres in the earth. The first one is atmosphere. We know that the thin gaseous envelope that is covering the earth is basically known as the atmosphere. This is where all the weather phenomena occurs, like rainfall, thunderstorm, and everything occurs in the atmosphere. And then we have the hydrosphere, which generally refers to a zone of liquid water on Earth's surface. Wherever water is present in liquid form, that particular regions are combinedly known as the hydrosphere. So hydrosphere exchanges water to the atmosphere in the form of vapor. Water in the liquid form evaporates and reaches the atmosphere in terms of vapor form. So it has mass transfer. There is mass transfer between hydrosphere and the atmosphere, and also in the form of precipitation. The condensed water vapor from the atmosphere comes back to the hydrosphere as well. So the mass exchange occurs between the hydrosphere and atmosphere in different phases of water. And there are also energy exchanges, like during the conversion from liquid to vapor, there is the release of latent heat of vaporization. And during the condensation of vapor back to liquid, there is latent heat of condensation, etc. So there is constant transfer of mass and energy between these different spheres. So hydrosphere is wherever the water is present in the liquid form, those regions are combinedly known as the hydrosphere. And also the ocean circulation generally transports heat from the equator to the poles. So equator is generally the region like this. Equator is around 0 degree. So this region is generally warmer compared to that of the polar regions, which is like these tips in the earth. So ocean circulation is generally carry warm water from the equator towards the pole. So heat transfer also occurs within the hydrosphere and also between the hydrosphere and atmosphere. And then we have the cryosphere. Cryosphere is where the water is present in solid form or in the form of ice. So hydrosphere is where water is present in the form of liquid, and cryosphere is where water is found in the form of solid. So cryosphere is a zone of solid ice on the Earth's surface. So this modifies the Earth's climate by reflecting the incoming solar radiation back to space. So ice is something which is having very high reflectivity. So the melting of ice, which is actually considered as a consequence of climate change, is actually leading to an increase in temperature, because ice helps in reflecting back the incoming solar radiation, or it helps in maintaining the temperature of the earth by reflecting the radiation back. So when you say the ice is melting, it means like more radiation is being absorbed by the earth. So cryosphere plays a major role in the climate change or whatever we are talking about. And then we have the biosphere. Biosphere is where all the living organisms live, including the plants, marine organism, and then us humans. So this is basically the zone of living system. This affects the atmospheric composition through the natural process like respiration, photosynthesis, and also like forest fires, etc. And also as humans are also part of the biosphere, anthropogenic greenhouse emissions from the biosphere also adversely affects the climate. And then the fifth one, we have the lithosphere. Lithosphere is a region of, it basically refers to the surface of the earth, the rocky region constituting the upper region of the solid earth, where all of us like lives. And this contains volcanoes, mountain formation, mountains, and all those. That is the lithosphere. So all these zones interact with each other and transfer both heat and mass between each other. So these are the fears that influences the climate that we are talking about. Now we will go a little more detailed into the atmosphere. So as I said, atmosphere is the thin gaseous envelope surrounding the earth, surrounding the solid earth. Thin gaseous envelope surrounding the earth. As we can see in this figure, this light blue line is basically our atmosphere. So compared to the total radius of the earth, the atmosphere is very small. It is like a thin blanket of air that is covering the earth. It is very thin. So this is basically a thin gaseous envelope surrounding the earth. It basically extends to hundreds of kilometers. It extends to hundreds of kilometers, but almost 99% of its mass is found within the 30 kilometer, in the initial 30 kilometers. 90% of the mass lies in the first 30 kilometers. Even though the atmosphere extends to hundreds of kilometers, almost 99% of the mass is confined to the first 30 kilometers. And this layer is generally transparent to the incoming solar radiation. Transparent to the incoming solar radiation. And it is opaque to the outgoing long wave radiation. So I'll just elaborate a little bit on this particular aspect. So the solar radiation that is coming from the sun is basically of wavelength, of very short wave wavelength, or the wavelength range falls in the short wave region of the electromagnetic spectrum. So the atmospheric gases is generally transparent to the incoming short wave radiation. So every gas molecule has a particular wavelength range in which it absorbs the radiation that is incident on it. So only a certain only wavelengths or only radiations of certain wavelengths excites the gases, excites the atmospheric gases. So if the radiation incident on a particular gas is not like some radiations pass through the atmosphere without interacting with the atmosphere or without heating the atmosphere. So generally the incoming solar radiation are transparent to the atmosphere, which means the solar radiation doesn't heat the atmosphere as it passes through the atmosphere and reaches the earth. Whereas once the solar radiation reaches the earth gets heated up and it starts re-emitting radiation in the long wave region of the electromagnetic spectrum. So our atmosphere is opaque to the outgoing long wave radiation, which means even though it doesn't interact with the incoming solar radiation, once the solar radiation is incident on the earth absorbs the energy, it acquires a particular temperature and starts re-emitting the radiation, which is generally in the long wave region of the electromagnetic spectrum. So our atmosphere is opaque to this particular wavelength or this outgoing long wave radiation. So whatever is being emitted from the earth is interacts with the atmosphere and actually heats the atmosphere. So the reason for the temperature that we see in the atmosphere is not the source of heating of the atmosphere is generally the outgoing long wave radiation from the earth, not the incoming solar radiation. So just to know what is the wavelength range at which the earth and sun emits radiation, we can use the Wien's displacement law. So Wien's displacement law generally tells you, so any body which is having a temperature greater than 0 emits radiation in a particular wavelength range. So this is basically a property of its temperature. So that particular this is basically given by the Wien's displacement law, which is lambda max into T is equal to C. C is basically a constant which is having a value of 2898 micrometer Kelvin. So suppose if we know the temperature of a particular object, we can find the maximum wavelength at which that particular body emits the radiation. So let's see in case of sun, what is the wavelength at which the sun emits radiation. So in case of sun, let's consider the temperature as 6000 Kelvin. Approximately I am giving you the value. Suppose the temperature of the sun is 6000 Kelvin. Can you calculate the lambda max, which means the wavelength at which the sun emits radiation? Yeah. So calculate the value of lambda max, and can you tell me what is the value? So lambda max will be the constant value, which is 2898 micrometer Kelvin divided by T. So as I have already given you the value of sun's temperature, which is 6000 Kelvin. So can you calculate and tell me what is the lambda max value in case of sun, the maximum wavelength at which sun emits radiation? Yeah, 483 nanometer. Is there any other answer? Yeah, so most of the people have got 483 nanometer. Can you tell me which range of the electromagnetic spectrum does it falls to? 483 nanometer is like which range it will come in the electromagnetic spectrum? Let's consider 500. If it's 500 nanometer, so this basically falls in the visible range of the spectrum. So the answer is coming as 483 nanometer. Yeah. So the answer is 483 nanometer. It basically falls in the visible range of the spectrum. Now in case of Earth, this is in case of Sun, right? Lambda max. This is the wavelength at which the Sun emits its radiation. Now in case of Earth, if we consider the temperature of the Earth as 20 degrees Celsius, so you have to convert it into Kelvin before doing the calculation. Suppose T is 20 degrees Celsius. Can you tell me what will be the value of lambda max? So in case of Sun, we got the sun emits radiation in the visible range of the spectrum, and the maximum wavelength is around 483 nanometer. Now let's see in case of Earth, what is the wavelength in which the Earth emits radiation. Yeah, towards blue. Visible is correct. So it's a visible only basically. Yeah. Now in case of Earth, what is the wavelength range in which Earth emits radiation? Yeah. So in case of Earth, it will be 20 plus 273, which is 293 Kelvin. 93 Kelvin, and it will be 2898 micrometer Kelvin divided by 293. This will be equal to 9.89 into 10 raised to minus 6 meter Kelvin, or we can write 9890. Yeah. So this generally falls in the infrared region of the spectrum. So this is basically a comparatively higher wavelength compared to that of the incoming solar radiation. So when we talk about the incoming solar radiation, we say incoming short wave radiation. And when we talk about the outgoing long wave radiation, outgoing radiation from the Earth, we generally refer to it as outgoing long wave radiation. So I think now you understood why we are saying that the incoming solar radiation incoming solar radiation is in the short wave region of the spectrum. As we saw, it's in the visible region. And when we talk about outgoing radiation from the Earth, we refer it as long wave radiation. So this falls in the infrared region of the spectrum. Okay. So the atmospheric gases or the atmospheric gas molecules are generally transparent to the incoming short wave solar radiation, and it is opaque to the outgoing long wave radiation. Okay, I guess it is clear. So the atmospheric gases interact with this outgoing long wave radiation and absorbs it and causes what is generally known as the greenhouse effect. So the atmospheric gases which is transparent to the incoming solar radiation atmospheric gases which is transparent to the incoming solar radiation incoming short wave solar radiation interacts with the outgoing long wave radiation from the earth outgoing long wave radiation from earth and causes what is known as the greenhouse effect. Okay, I think it is clear. So that is about the atmosphere. Atmosphere is a thin gaseous envelope which is surrounding the earth. It is hundreds of kilometers in height, but almost 99% of the mass is confined to the first 30 kilometers, and it is gently transparent to the incoming solar radiation, and it is opaque to the outgoing long wave radiation. And from Wien's displacement law, we found that the solar radiation which is coming towards the earth falls in the short wave visible range of the electromagnetic spectrum, and the radiation that is being re-emitted from the earth falls in the long wave radiation of the electromagnetic spectrum. We calculated the values using the Wien's displacement law, which is given as lambda max into T is equal to a constant. And what is basically greenhouse effect? The atmospheric gases, which is gently transparent to the incoming solar radiation, allow the solar radiation to pass through it without interacting or creating a warming in the atmosphere. And once it reaches the surface of the earth absorbs it and attains a temperature and starts re-emitting the radiation in the long wave region of the electromagnetic spectrum, which is basically absorbed by the atmospheric gases and causes what is known as the greenhouse effect. Now let's have a look at the vertical structure of atmosphere. What are the different layers in the atmosphere? So this classification has been done based on the thermal structure of the atmosphere, based on how the temperature in the atmosphere varies. So based on the temperature variation, we have 4 different layers in the atmosphere, which are the lowest layer, which is known as the troposphere, the second layer, which is known as the stratosphere, then we have mesosphere, and the fourth one we have the thermosphere. So the lowest one is the troposphere. In the troposphere, so we can see in the figure the lowermost layer. This is the surface of the earth. So the x-axis basically shows you the temperature variation, and the y-axis shows you the height from the surface of the earth. So in the troposphere, as we can see, the temperature at the surface is around 18 degrees Celsius, and as we come up along the troposphere, the temperature is decreasing with respect to height. Then we reaches a boundary which is basically known as the tropopause. So in the tropopause, the temperature decreases with respect to height at an average lapse rate of 6.5 degrees Celsius per kilometer. So dt by dz, or the rate of change of temperature with respect to height in the troposphere, is given by 6.5 degrees Celsius per kilometer. As we go up at least 1 kilometer in the troposphere, there will be a decrease of 6.5 degrees Celsius in temperature. So this rate of change in temperature with respect to height is generally known as lapse rate. And the average lapse rate in the troposphere is 6.5 degrees Celsius per kilometer. It is minus 6.5 because there is a decrease. Minus 6.5 degrees Celsius per kilometer. So in the troposphere, temperature decreases with respect to height at an average lapse rate of 6.5 degrees Celsius per kilometer. And the troposphere contains all of the water vapor in the atmosphere. Most of the water vapor in the atmosphere is in the troposphere only, in this lowermost tropospheric layer only. And tropospheric air accounts for 80% of the mass of the atmosphere. And the boundary separating the troposphere and the next layer, the stratosphere, is known as the tropopause. As you can see, there is a thin dotted line in this point when the temperature starts, when the temperature profile starts changing. So that thin white dotted line is known as the tropopause. It is basically the boundary that is separating the troposphere and the stratosphere. And the thickness of the troposphere is determined by the amount of solar energy received during that particular period. So this is generally that particular period over that particular area. So if we talk about equator, where there is a larger incoming solar radiation, or the region which receives more energy compared to that of the polar regions, tropopause is at a higher height. So as more solar energy is received by the troposphere, the air in the troposphere expands, and because of that, the height of the tropopause increases. So suppose in the equator, the tropopause is at a height of 12 kilometers. In the polar regions, the height of the tropopause will be at a much lower height. For example, maybe 8 kilometers. So over the equator, so the thickness of the troposphere is generally determined by the amount of solar energy received. So at the equator, tropopause is at a height of around 16 kilometers, and over poles, which comparatively receives less energy, at such a height of 8 kilometers. And the amount of solar energy received by the earth also changes with respect to season. So can you tell me, like, during which season, like summer or winter, will we have highest tropospheric height? Which season we will be having a higher height of the tropopause, or which season the tropopause will be found at a higher height? So this is based on geography, like equator will be having a higher tropopause height compared to that of the polar regions. Now based on seasons also, can you tell me during which season we can expect the tropopause to be higher, and in which season we can expect tropopause to be lower? Yes, correct. So during summer season, when we receive more amount of solar radiation, the tropopause is found at a higher height. And during winter, when we receive, yes, exactly. And during winter, when we receive less amount of solar radiation, the height will be a little lower. Now, if we look at the temperature of the tropopause, so can you tell me the where the tropopause temperature will be higher, like over the equator or at the polar region? So we already told, like in the equator, the tropopause is found at a higher height. Now if we look at the temperature, which region will be having a higher tropopause temperature, equator or the poles? Based on the height, I think you can tell. And we already told that so over equator, what it will be, higher or lower? Over the equator, the tropopause temperature will be okay. So I told you the temperature of the troposphere. Yeah, exactly. So due to the like more if the tropopause is at a higher height, it means more lapse rate, like it is traveling more distance and the temperature is getting lower and lower as the height increases. So at 8 kilometer, the temperature will be comparatively higher than that of what is found at 16 kilometer, which means at the polar regions, the temperature will be higher. The tropopause temperature will be higher compared to that of the equator. This is basically due to the height, because more lapse will be happening when the tropopause is at a higher height. So at 16 kilometer, it will be, the temperature will be surface temperature minus 16 into 6.5. Whereas over the poles, it will be surface temperature into uh, 8 into 6.5. So because over the equator, it is at a higher height, the tropopause temperature will be lower. Is it clear? So when we talk about the height of the tropopause over the equator, it is at a higher height. Now when we look at tropopause temperature, because of the higher lapse that is happening due to higher height over the equator, the temperature will be minus 80 degrees Celsius, whereas over the polar regions, the temperature will be minus 50 degrees, because this is found at a higher height. This is the temperature at a height of 16 kilometer, whereas this is the temperature at a height of 8 kilometer. So this will be lower compared to that of, I hope it is clear. So that is all about troposphere. Troposphere is the lowest atmospheric layer. This is the region where the temperature actually decreases with respect to height, and the average lapse rate is given by minus 6.65 degrees Celsius per kilometer. And this lapse rate also fluctuates based on day to day and season to season. And most of the water vapor is found in the troposphere. Tropospheric air accounts for 80% of the mass of the atmosphere, and the boundary separating the troposphere and stratosphere is known as the tropopause. The thickness of the troposphere or the height of the tropopause is determined by the amount of solar energy received. So it is basically tropopause is found at lower heights over the poles and at a higher height in equator. And when you look at the tropopause temperature, the tropopause temperature is higher over the poles compared to that of the equator. I think it is clear. Now we will go to the second layer in the atmosphere, which is stratosphere. So in the stratosphere, as we can see, so stratosphere starts from here. So from here, if we look at, the stratosphere is actually having an increase in temperature with respect to height, different from that of the troposphere. Now the second layer is the stratosphere. Stratosphere is actually having increase in temperature with respect to height. Stratosphere is having an increase in temperature with respect to height. It extends from the top of the troposphere up to a height of 50 kilometers from the ground. Up to 50 kilometers this extends. And this layer is extremely dry. Extremely dry in the sense water vapor content is very less or it's almost absent. So this particular layer is having extremely dry and ozone rich air. So this region is actually having ozone molecules in this. This is the presence of ozone molecules is the reason behind the observed temperature pattern. Ozone rich because of the ozone temperature increase with respect to height is basically due to the presence of ozone. So the level of maximum ozone concentration is generally observed at a height of 25 kilometers. We can see here ozone maximum is written at a height of 25 kilometers. So what happens is that the ozone molecules present in the stratospheric layer absorbs the incoming shortwave radiation. So generally the atmospheric molecules, the atmospheric gas molecules are transparent to the incoming solar radiation. We have been discussing that so far. So but in the case of ozone molecules, the peculiarity of ozone molecules is that it is not transparent to the incoming solar radiation, but it absorbs the ultraviolet region of the spectrum. Like whatever radiation is coming, it generally absorbs the wavelength, absorbs the radiation in the ultraviolet region of the spectrum. So because of the absorption of the ultraviolet radiation, it heats up the atmosphere over the region wherever the ozone molecules are present. So because of that, we are having this particular pattern of temperature increase with respect to height in the stratosphere. So the ozone, even though the ozone maximum is present at a height of 25 km, the highest temperature is actually found at 50 km. So if ozone molecules are actually absorbing the incoming shortwave radiation, the highest temperature should be found at this particular height, right, around 25 km. But this is actually happening at 50 km height because um, even though the ozone molecules are very less in that particular height, it absorbs most of the incoming solar radiation and it heats up the atmosphere at that particular layer. As we go down in the atmosphere, the amount of radiation reaching the lower levels are comparatively less compared to the top of the stratopause or top of the stratosphere. That's why we are having a higher temperature at the stratopause compared to the lower level layers of the stratosphere where more ozone is present. So that is the peculiarity of stratosphere. Yeah. The boundary near the stratosphere, the top of the stratosphere around 50 km, which separate the layers of stratosphere and mesosphere is known as a stratopause. Like the tropopause, in the top of the stratosphere is known as stratopause. It basically separates the stratosphere and the above layer mesosphere. So mesosphere is again the third layer. In the mesosphere, again the temperature decreases with respect to height because no absorption of solar radiation is happening in that particular region. And the mesopause is the region where we find the lowest temperature in the atmosphere, around minus 80 degrees Celsius. So the coldest region in the atmosphere is the mesopause, where the temperature goes to around minus 80 degrees Celsius. That is mesosphere, and above the mesosphere we have the thermosphere. So in thermosphere the atmospheric gases are very much rare, and whatever remaining gas molecules are present that interacts with the incoming solar radiation and undergoes process known as photodissociation and photoionization. And because of these processes or because of these interactions, we have very high temperature in the thermosphere. As we go up in the thermosphere, the temperature keeps on increasing. This is basically due to these chemical processes that are happening. So yeah, so that is about the different layers of the atmosphere: troposphere, stratosphere, mesosphere, and thermosphere. Troposphere, the temperature is decreasing with respect to height at a rate of 6.5 degrees Celsius per kilometer. In the stratosphere, the temperature is increasing with respect to height. This is basically due to the presence of ozone, which absorbs the incoming shortwave solar radiation, mainly in the ultraviolet region of the spectrum. And then we have mesosphere. Again, the temperature decreases with respect to height, and mesopause is the coldest region in the atmosphere where the temperature goes below around minus 80 to minus 90 degrees Celsius. And in the thermosphere, very few atoms or molecules are present. So these absorb small amount of these molecules, whatever is present, undergo process known as photoionization and photodissociation. So this is basically based on the thermal structure of the atmosphere, like how the temperature is varying in the atmosphere. We have classified it into 4 different layers. Now, if we are classifying based on the composition, we can classify the atmosphere into 2 different layers, which is homosphere and the heterosphere. Homosphere is from the troposphere to the thermosphere, where we have most of the gas molecules in the neutral forms. And above the homosphere, we have the heterosphere, which is basically the thermosphere to the top of the atmosphere. So this is called heterosphere because there we have ions, atoms, molecules, everything. Because of the interaction of solar radiation with the atoms, it dissociates into ions, the molecules dissociate into atoms, like that. All these kind of reactions occur in the heterosphere or the thermosphere. So that's why till the thermosphere we can call it homosphere, and above the thermosphere we can call it heterosphere. And now, based on the electrical properties, we have the ionosphere, which extends from 60 kilometers to the top of the atmosphere. From 60 kilometers to the top of the atmosphere is what is known as the ionosphere. This have within the ionosphere we have D, E, F and F layers, etc. So these are basically based on the concentration of ions present in these particular layers. So that is 3 different types of classification based on thermal structure, based on the composition, based on electrical properties. Based on thermal structure is what we generally use for our studies. So that is mostly used for most of the studies. And now we will have a look at the composition of the atmosphere. We have been telling like atmosphere is composed of gases, this is a thin gaseous envelope, etc. So what all gases are actually present in the atmosphere? So this basically gives you an idea how much what all are the different molecules present in the atmosphere. So basically the diatomic nitrogen and oxygen are the dominant gases in the atmosphere. The most dominant gas in the atmosphere is nitrogen, which is present around 78.08%. And then we have oxygen, which is present 20.95%. So this almost constitutes like 98% of the atmosphere. Almost 98 to 99% of the atmosphere is basically nitrogen and oxygen, and all other gases are like very less. And the third most abundant is the argon gas, which is an ideal, it's just a neutral, what is it called? It is an inert gas. It is present of almost 0.93%. Then we have water vapor. So in case of water vapor, we can see the volume is actually varying. Water vapor is a variable constant, which means geographically, if we look at a particular, some regions will have higher amount of water vapor, and some regions will have very lower amount of water vapor. For example, if we look at the tropic regions or monsoon regions, tropical regions, we have very high amount of water vapor, and when we go to dry, arid regions or desert-dominated regions, over those regions, the amount of water vapor will be very less. So over humid regions, we will have very high percentage of water vapor, whereas when we go to arid or desert regions, we will have very less amount of water vapor. So water vapor is basically a variable constituent in the atmosphere. Then we have carbon dioxide, which is present around 380 parts per million in the atmosphere. Then the other gases like neon, helium, methane, etc. So can you just tell me what are the greenhouse gases that are actually present in this from this table? What are the greenhouse gases that are present in the atmosphere? Can you tell me? What are the gases that we actually call as yeah, water vapor, carbon dioxide, methane, all these gases are greenhouse gases basically. So carbon dioxide is an important greenhouse gas that is entering the atmosphere at a greater rate than it is being removed. That is the reason for take this global warming or greenhouse effect that we generally, that the adverse effects are mostly caused by the higher. So these are the we require these greenhouse gases. As I told you, greenhouse gas effect is very much important. But the issue is when it exceeds a particular amount, when it is exceeding the required amount, or whatever is entering the atmosphere is actually not leaving the atmosphere. So that is the reason we experience global warming and all these adverse effects of climate change. Now let's try to see what of the greenhouse gases were not present in the atmosphere. What will be the temperature of the earth? So we will try to see that why greenhouse gases are important and why this is causing this much of an issue. Let's just try to find that. So suppose greenhouse gases were not present in the atmosphere. Suppose greenhouse gases are not present in the atmosphere, what will be the temperature? What will be the temperature of the earth? So in that case, it means whatever the incident radiation in the earth's atmosphere, in the earth's surface, I incident is going back. Whatever radiation is incident on the earth's surface is actually re-emitted back. Yeah. So in that case, I incident will be I emitted. Now let's find out what is I incident first. I incident is the amount of solar radiation that is reaching the surface of the earth. Okay. So this we can calculate with the help of Stephen Boltzmann. Stephen Boltzmann law shows E is equal to sigma T raised to 4, where T is the temperature of the body that we are considering. T is the temperature, E is the energy emitted by that body, and sigma is the Stephen Boltzmann constant, which is given by 5.67 into 10 raised to minus 8. Okay, so let's this time we will consider a more accurate value of sun's temperature, which is 5,772 Kelvin. So suppose this is the temperature of the sun. We know the value of sigma is 5.67 into 10 raised to minus 8. The unit is watt meter raised to minus 4 Kelvin raised to minus 4. Yeah. 5.67 into 10 raised to minus 8 watt meter raised to minus 2 Kelvin raised to minus 4. T is the temperature in Kelvin and E is the energy emitted per unit watt per meter square. Okay. So suppose the temperature of the sun is 5,772 Kelvin. What will be the energy emitted by the sun? Per unit area. So it will be 5.67 into 10 raised to minus 8 into temperature will be 5,772 72 Kelvin. Yeah. Can you tell me what will be the value? Energy emitted by the sun. Yes, 6.29 into 10 raised to, yeah. So it will be around 6.29 into 10 raised to 7 watt per meter square. The value will be 6.29 into 10 raised to 7 watt per meter. So this is the energy emitted per unit area from the surface of the sun. Now this is per unit area. So what will be the total energy emitted from the sun surface? Total energy is given by energy emitted per unit area into surface area. Surface area is 4 pi r square. Since sun is a sphere, surface area will be, the surface area of the sphere is given by 4 pi r square, and the radius of the sun is given by 6.9 into 10 raised to 8 meter. So the total energy will be 6.29 into 10 raised to 7 into 4 pi r square, which is 4 into 3.14 into 6.9 into 10 raised to 8 square. Yeah. So what will be the total energy? So this is a per unit area, what is the energy emitted from the surface of the sun. Now to find the total energy, we multiply it by the surface area of the sun. So in that case, what will be the total energy? Can you tell me how much you are getting? Total energy emitted from the surface of the sun. The Stephen Boltzmann law gives you the energy emitted per unit area. So in order to find the total energy emitted from the surface of the sun, we multiply that by the surface area of the sun, which is given by 4 pi r square, surface area of a sphere, and the radius of the sun is given by 6.9 into 10 raised to 8 meter. So in that case, what will be the total energy emitted from the sun's surface? Yes, 3.76. Yeah, so we will, in the next step, we will consider that also, like how much is coming towards that. So initially we are just considering how much is being emitted from the sun. Then in the next step, we will find like how much is actually reaching the earth. So this is the total energy emitted by the sun, which is coming around 3.76 into 10 raised to 6 volts. So this is the energy emitted from the sun's surface. Now we have earth over here. So the energy emitted from the sun is getting radiated like this from all sides. And when it reaches earth, it has to travel a distance of around 150 into 10 raised to 9 meter. So this much yeah. Oh, sorry. Okay, 10 raised to 20. Thank you. Thank you for pointing it out. So it is 3.76 into 10 raised to 26 watts. Okay. So like this radiation that is being radiated from the sun has to travel a distance of around 150 into 10 raised to 9 meter and then reach the surface of the earth. So the amount of radiation that is reaching the surface of the earth per unit area, energy received in the top of the atmosphere per unit area equal to 3.76 into 10 raised to 26 divided by, so we are considering a sphere of this much radius. We are considering a sphere which is having a radius which is equal to the distance between the sun and the earth. So in that case, we are per unit area we are considering. So we will do by 4 pi r square. And here r is the distance between the sun and the earth. So it will be 3.76 into 10 raised to 26 divided by 4 pi into r. R is 150 into 10 raised to 9 the whole square. How much will be the value? Can you tell me? So the amount of radiation, the energy received in the top of the atmosphere per unit area is given by 3.76 into 10 raised to 26 by 4 pi r square. Here we are considering a sphere which is having a radius equal to the distance between the sun and the earth. So r is given by 150 into 10 raised to 9 the whole square. Yeah. 1330 around we are getting. One three three zero watt per meter square. This value is basically known as a solar constant. The amount of energy reaching the top of the atmosphere per unit area is known as a solar constant, and it is having a value of approximately 1330 watt per meter square. Now we know what is the amount of radiation incident on the earth. So we started with I incident, right? So we now know what is the value of I incident. The amount of radiation I incident is equal to 1330 watt per meter square into pi r square. Here we are taking pi r square because so the solar radiation is falling on a particular disk. So this is sun, and here we have earth. Only this region of the earth is being illuminated by the sun, right? It is kind of a disk. So the area of this disk is given as pi r square. And in this case, r is the radius of the earth. So I incident is equal to, this is per unit area, into area is the area of the sphere that is being illuminated by the sun's rays, which is given by pi r square, where r is the radius of the earth. So I incident is given by 1330 into pi r square. Now we need to find what is I emitted. I emitted is given by, so energy per unit area is sigma T raised to 4 according to Stephen Boltzmann law. The energy emitted per unit area from a body having a temperature of T, temperature T is given by sigma T raised to 4, where T is the temperature of the earth, into total energy is 4 pi r square. So here again r is the radius of the earth. How much energy is being re-emitted from the earth? So total surface area of the earth is 4 pi r square. So per unit area, so energy emitted per unit area given by the Stephen Boltzmann law into total area of the earth, which is 4 pi r square. So we are considering the case in which I incident is equal to I emitted. That is, whatever incoming solar radiation is, whatever solar radiation is coming from the sun, it is directly getting incident on the surface of the earth. The earth is absorbing all of its energy and then attaining a temperature and then re-emitting all the energy back to the space. So we are considering a condition like that. So it will be 1330 into pi r square is equal to sigma T raised to 4 into 4 pi r square. So basically we want to find the temperature of the earth. We are trying to find out, suppose the greenhouse gas effect was not present, what will be the temperature of the earth. That is, whatever energy is being re-emitted from the earth, nothing is being absorbed by the atmosphere. The atmosphere is acting transparent to the outgoing long wave radiation and it is escaping to the space. So basically we want to find the value of T, which is the temperature of the earth. So here 4 pi r square and 4 pi r square will be gone. So this is 1330 by 4 into sigma, which is 5.67 into 10 raised to minus 8, the whole raised to 1 by 4. This will be the temperature of the earth. Suppose all the energy incident on the earth is getting re-emitted back to the space. This will be the temperature of the earth. Can you calculate and tell me what will be the temperature? What will be the temperature of the earth if all energy that is being incident on the surface of the earth is getting re-emitted back to the space? Yeah, it is coming around 276 Kelvin. 276.7 Kelvin, which is basically, if we write it in terms of degrees Celsius to get a more better idea or better visualization, that is around minus 3.7 degrees Celsius. If the temperature of if the temperature of the earth would have been this value, then life would not have been possible in the earth. So because of the greenhouse effect only, so this I re-emitted as whatever energy is being absorbed by the earth, all the energy is not actually being gone, is not going back to space. Some of the energy is retained in the atmosphere because of the greenhouse gases. So because of that only we are having an average temperature of around 15 to 20 degrees Celsius in the surface of the earth. So if greenhouse gases were not present in the atmosphere, the temperature of the earth would have been minus 3.7 degrees Celsius. And we can complicate this equation, or we can add more terms like albedo and all those things. Not all incident radiation will be absorbed by the earth. Some will be reflected back. So if we are considering the reflected back radiation, then the equation will become, so we are considering that in from the I incident, some is getting reflected back. Some is getting reflected back. Suppose the I reflected or the albedo is given by, some of it is getting reflected back, then the equation becomes S by 4 into 1 minus alpha is equal to sigma T raised to 4, where alpha is the albedo. Albedo means the reflectivity of the earth. So this albedo is having a minimum value of 0 and maximum value of 1. 0 means all is like nothing is reflected back, all is absorbed. That is what we considered in the initial stage. And initially we considered that the albedo is 0, that is all energy is being absorbed by the earth. So 1 means all is reflected back, nothing is being absorbed by the earth. So the Earth has varying albedo surfaces like desert region, vegetation, ocean, ice, etc. So generally we have an average albedo value after considering all different surfaces as 0.3. So if we are including the albedo, also the equation becomes S by 4 into 1 minus 0.3 is equal to sigma T raised to 4. S is the solar constant that we calculated, this value 1330 watt per meter square. That is basically S. So the equation becomes like this. So albedo is how much energy is being reflected back to space before getting absorbed by the earth. So generally the earth is having an albedo of 0.3. So if we consider the albedo, then what will be the temperature? Can you do the calculation again and tell me? So it will be again 1330 by 4 into 1 minus 0.3, 5.7 into 10 raised to minus 8, the whole raised to 1 by 4. So if we consider albedo also, then what will be the temperature? Okay, sorry, it is plus 3.7, right? Okay, I wrote that wrongly as minus 3.7. Thank you. Plus 3.7. Yeah, you are right, it's plus, not minus. In that case, the temperature will be 253 Kelvin. So then it becomes, it will be around minus 20 degrees Celsius. So the temperature would have been minus 20 degrees. So this would have been the temperature of the Earth. The greenhouse gases would not have been present over the atmosphere. Whatever is coming from the solar radiation some will be reflected back, and whatever is being re-emitted from the Earth's surface will be going back to the space without getting absorbed by the atmosphere. So in that case, the temperature of the Earth will be minus 20 degrees Celsius. So the greenhouse gases are actually very much important for sustaining life in the Earth. Then why we are worried about this climate change and everything? Why we are talking that greenhouse gas effect is bad and we are facing climate change and everything? So the issue is that after the industrial revolution or during the pre-industrial time, the amount of carbon dioxide concentration in the atmosphere was around 278 parts per million. So we can see the x-axis shows you the years and y-axis shows you the carbon dioxide concentration. So this was the amount of carbon dioxide concentration that was present in the atmosphere. So this was the amount of carbon dioxide concentration that was present in the atmosphere during the pre-industrial time. And after the industrial revolution, or in the last 2 decades, if we say in the last years, we can see from after 1950, we can clearly see an increase in a steady increase in the carbon dioxide concentration present in the atmosphere. So from 278 parts per million, it has become around 470 part per million in the atmosphere. So that it is almost 50% increase in carbon dioxide is actually seen. So in the atmosphere, there are a lot of natural processes by which we can remove the naturally emitted or remove the carbon dioxide concentration, like through respiration, transpiration, and by dissolved. So many of the atmospheric carbon dioxide get dissolved in the oceans that are present in the Earth surface. So ocean is the largest sink of carbon dioxide that are present. So what is actually happening is the amount of carbon dioxide that we are emitting through the anthropogenic activities are not actually getting removed from the atmosphere. So whatever process, natural processes are there to remove the carbon dioxide is not becoming sufficient to remove the highly emitted carbon dioxide from all the anthropogenic activities. So due to this, after the industrial revolution, we are seeing almost a 50% increase in the atmospheric carbon dioxide concentration. So this is actually what is leading to climate change. So as I said, the presence of greenhouse gases is actually to absorb the outgoing long wave radiation and then maintain the Earth at a reasonable temperature. So what happens if this amount of greenhouses are more? It will start absorbing more radiation. So there is a minimum amount of radiation or minimum amount of carbon dioxide concentration that we require to maintain a reasonable temperature. So it becomes higher than what is required. It will eventually result in a higher temperature of the Earth's surface. So that is actually what is happening now. The carbon dioxide is not getting removed from the atmosphere and it is becoming excess and thus resulting in, and it is trapping heat in the atmosphere, thus leading to the rise in the mean temperature. And as a result of this, if we look at the temperature change that has happened over the past years, we can see that in the recent years, if you look at the black line, we can see, suppose if this is the mean, as we are talking the normal temperature or the normal value of the climatology of temperature is this. The zero line represents the normal value of temperature. In the recent years, we can see a clear deviation from the normal towards higher values. So in the last 2 decades, around 1.5 to 2 degrees Celsius increase in temperature is actually seen from the is that we are experiencing almost 1.5 to 2 degrees Celsius increase in global mean temperature. This is the result of the enhanced emission of carbon dioxide or other greenhouse gases. So greenhouse gases are actually good only if we are able to, like whatever we are emitting is actually being removed by the natural process. So now the issue is like water being emitted is not properly getting removed from the atmosphere. It is kind of accumulating over the atmosphere and then leading to trapping more outgoing longer radiation, and then leading to more warming and a higher global mean temperature. So that is what is climate change. I think I will stop it over here today. Is this data from ERA 5 or weather stations? So this is actually I have taken from the recent IPCC report. So they have IPCC has a group of models like SIMUPSETs and all where they it is actually from a group of models, not particularly from ERA5, not from weather stations. It is global mean temperature. So it is from a global model. The data is taken from, I think it is mostly an ensemble of various global models that are available. So we have like a group of models that we use for simulating various variables, temperature, rainfall, etc. So this is the average value, average of the values that is taken from different models. Yeah. Okay. Thank you. And I see a number of questions in the chat box. I'll just go through it. Yeah. So I think this question is clear because when we were considering that solid angle on Earth and everything, so we were considering only the disk um, when we considered how much is actually reaching the we multiplied it with pi r square, like the energy emitted per unit square per unit area from the surface of the Earth. We multiplied it by pi r square. So that is the area of the disk that is being illuminated by the solar radiation. So I think that thing is clear. Yeah. Is ozone anti-greenhouse gas since it blocks shortwave coming into troposphere and land? There is no, I haven't heard a term called anti-greenhouse gas. So ozone in the stratosphere is actually good because it reduces the incoming ultraviolet radiation. So stratospheric ozone is actually considered as a like that is actually required for um, our sustenance and all. But this ozone is actually present in the troposphere also. So the tropospheric ozone is actually not good. Tropospheric ozone is considered as a greenhouse gas. So tropospheric ozone so that is basically produced by the vehicle exhaust and all. Tropospheric ozone is not good. It actually lead to it is actually a greenhouse gas. Uh, it is a harm like it is not good for the atmosphere. But ozone in the stratosphere is actually fine. So that is actually we require the stratospheric ozone. We need to maintain the stratospheric ozone level. But the tropospheric ozone is not is actually a greenhouse gas which is actually harmful and it is having adverse impacts. Why ozone layers are found only in stratosphere? That so basically troposphere is actually having troposphere is very close to the surface of the earth and there the turbulence and vertical mixing is all very high. So if you look at like um, the gases will have a uniform composition. Like it will everywhere, if you look at it will be this 78% nitrogen and 20, like all along the troposphere. Vertically, you won't be able to see a difference. But stratosphere is comparatively more layered kind of thing. It is like more stratified because the temperature is actually increasing with respect to height and the vertical mixing is very less. The gases doesn't mix with each other. So because of that, the ozone molecules are stable because of the stability of that particular layer only. It is easy for the formation of ozone. So ozone generally forms from oxygen molecules by absorbing ultraviolet radiation only. So this process or this chemical reaction is more easier to happen in the stable stratosphere rather than the more turbulent troposphere. So in the stratosphere, when it forms, it is possible for it to form a layer and then um, it is possible for it to form a stable layer kind of in the stratosphere. In the troposphere, it is not possible because of the high vertical mixing or the high turbulence that is present and also due to the temperature profile over the troposphere. So this is a more stratosphere provides that more favorable condition for the formation of ozone because of its stability or that stratified layers or that stratified structure. So yeah, so that is the reason why ozone is only present in the stratosphere. And then it seems more counterintuitive because poles being warmer. So I'm not talking about the surface here. When I told you that the temperature at the tropopause in the poles is actually higher, I told. So it is actually happening at a higher height in the atmosphere. So that doesn't mean that the surface temperature is high over the poles. So this is actually happening at a higher level in the atmosphere. So it don't have anything to do with the surface. And even though so it doesn't affect the land below anything. So the temperature that we are getting is actually by decreasing as we go up. Suppose if we have a minus 10 degrees Celsius temperature at the surface, as we go up, it is decreasing and decreasing, and then we are getting a lower temperature. So that lower temperature is not going to affect the surface for surface temperature or anything. From the surface temperature only, we got that lower temperature in that particular height. So it doesn't have anything to do with the land below like land below. This is actually happening at a higher atmospheric layer. So that doesn't mean the pole is warmer or anything. So that is like I'm talking about a higher layer in the atmosphere. I don't know if that's clear. I think it is clear. Yeah, we cannot use median actually. Median just gives you like maximum which value is actually having the largest number of occurrences. So it's more we generally use mean only when we talk about the normal climatology or the normals are generally refers to the mean rather than median. Yeah, Pratap, you have anything to ask? You have raised your hand. I think that's all. If you have any other doubt, you can ask me. Something is not clear or you want me to explain it again, you can tell me. Or else we'll stop today's class. Thank you for attending. If you have something, you can ask. I hope if something is not clear, please do let me know. Yeah, thank you. Okay then. Bye. Thank you all for attending. We'll see you next week. Bye. Yeah, bye.